Okay, in the last video, we had derived this identity here, where r is the magnitude of any position vector raised to the nth power, and we're taking the Laplacian of that magnitude, and we derived this identity. And obviously, performing this operation is a lot shorter than having to take all those second derivatives and dealing with those. So these identities that we're deriving can really save you a lot of work. So we're taking some time to present these identities to you, and also the thinking that goes behind, so the logic behind the identities. And if you haven't seen the background in the previous videos, part of what we're doing right now doesn't make a lot of sense to you. So again, it's really worthwhile to get that background information, because we're going to keep incorporating that as we encounter more and more topics in vector analysis. What we want to point out in this video is that what we're doing here, we encountered this expression in the last video as we were obtaining this identity, and we were able to deal with this with no problem. What we want to point out is that we can sort of write out a general formula for this type of situation. That is, where we have our position vector r that's being multiplied not just by a scalar, but by a function of r itself. So we have this kind of a situation. We have del dot some function of r times the position vector r. Now, in different textbooks, you might see them writing this as a scalar function phi of r. It means the same thing, of course. We just pointed out to you because you might see it written different ways in different mathematics and engineering books. And if you've watched our previous videos on vector identities, I think this is from the third example, you know that this can be written out like this, where we take the gradient of the scalar, take that gradient vector, take the dot product of that with this vector, plus you have the gradient of the scalar times del dot that particular vector. This is true whether it's the position vector or not. This is a general formula here, but when we are dealing with the position vector, we know its divergence is 3. So this is equal to 3 times the scalar quantity plus this expression. And if you have watched the previous videos, hopefully now you're aware that we can rewrite this, that del operating on this scalar quantity, because the function of r is equal to the derivative of that function of this r function times the gradient of r. And for the position vector, the gradient of r, which is the magnitude of the position vector, that is equal to this, which is the unit position vector. Of course, we can write it like this: position vector divided by its magnitude. So this is equal to, from here, of 1 over r times the derivative here times the position vector r. This can be rewritten as this. Now, what are we supposed to do with that? We're supposed to take this and take the dot product of it with the position vector. So let's do that. Take that dot product, make some room here, because r dot r is r squared. And r squared divided by r, that's just going to equal r times f prime of r. So that's what this term is. It's r f prime of r. So let's write that in. R times f prime r. And that's equal to then this. So you see here then is a general formula when we have a position vector multiplied by a scalar quantity, but that scalar quantity itself is some function of r. It's equal to this. So for example, suppose we have this problem. We were taking this, del dot n r to the n minus 2. So that's our scalar quantity times r. We would say, well, that would be equal to 3 times the scalar quantity plus r times its derivative, which would be n times n minus 2 times r to the n minus 3. But r times r to the n minus 3 is r to the n minus 2. So here we have 3n times this minus 2n times this. So that's going to be equal to n times n plus 1. And there it is. It just pops right out for us. We obtained the same expression in the last video, but we didn't use this general formula approach, so it took a lot more work to get there. So you can see that once you become familiar with these operations and sort of the thinking that goes behind them, it can really lighten your workload as you have to perform these different types of operations. Suppose, for example, we had this problem where we have del dot r to the n minus 1 times this. So our formula was it's 3 times the scalar quantity plus r times the derivative of the scalar quantity. So this would be equal to 3 times r to the n minus 1 plus r times its derivative, which would be n minus 1 times r to the n minus 2. So we're multiplying this by r, so that's going to be n minus 1. So here we have 3 times r to the n minus 1 minus r to the n minus 1. So here we're going to have n plus 2 r to the n minus 1. As you can see, it's a heck of a lot easier and a heck of a lot quicker to figure this out using our formulas that we devised along the way, rather than having to go through all the steps involved that you've seen us do in previous videos. But anyway, that's it for this video. Come back and join us for some more videos, and we'll try and work some more problems.